8.9, and then we'll go to chapter 9. Chapter 9, hardest chapter in the book.
I doubt it.
Okay. So when we look, chapter 9 is not the hardest chapter in the book. Easiest sections we're going to cover this whole semester.
What is the hardest chapter?
Chapter 10.
Really?
Oh, no.
Yeah.
Why?
Infinite series.
What?
Infinite series. It takes so long to add up an infinite number of numbers. It's
Oh,
so hard.
okay. It's like infinite time.
You have to just keep adding and adding and adding.
I can just use a calculator.
Yeah, you still have to add and add and add. Okay, so we see this. We see this integrand. It is an improper integrand, but we don't notice that it's an improper integrand because there's no infinity in the limits of integration. But which limit of integration gives division by 0? Araceli, which one gives division by 0? What?
Huh?
Huh? Which limit of integration gives division by 0? 0. Thank you, Araceli. So if you plug in 0, you end up with division by 0. Anyone not see that? So if we plug in 0, we have e to the 0, which is 1. 1 minus 1 is 0, so we have division by 0.
Yeah.
That means we have a VA, vertical asymptote. It's undefined at 0. That means vertical asymptote. So that immediately tells us that we need to convert to a limit. We know it's an improper integral. We want to make it a definite integral, so we're going to put in a c there. So we're going to go from c up to natural log of 3. Everything in the integrand at this point just staying the same. Just staying the same. And what is c going to approach?
0.
0 from the right-hand side. Is that clear to everybody?
Yes. Could you explain why? Like how do you,
I can explain it so clearly. So here is the interval. There is natural log of 2. There is 0. So those are our limits of integration. Oh, natural log of 3, not 2. So there is our interval. This side is not a problem, right? Natural log of 3 doesn't cause anything fishy. 0 causes this vertical asymptote. So we've got this vertical asymptote right there. So we are basically picking a c value that's in between the two. So over here on the right-hand side, we have these rectangles that are forming a definite integral. So we're imagining these rectangles. And c has to get closer and closer to 0 for us to get this whole area. So what side of 0 is c coming from? The right-hand side. So we always have to, if we're approaching the left endpoint, we're coming from the right. If we approach the left endpoint, we're coming from the left. We always stay within the interval.
Can you say that one more time?
Is that a legitimate question?
No.
Yeah, then no. So yeah, we always have to come from within the interval. If we're coming to the left endpoint, we're coming from the right. And if we're going to the right endpoint, we're coming from the left. So if you're ever in doubt, draw the interval and look at where your asymptote is, and you have to just approach it from the correct side. You have to be within the interval as you approach that asymptote. Always within the interval. All right, so that is why we are going to convert it to that. Now we have to use integration, and what technique should we use? I think I just heard it. U sub? Did I hear that? Or am I hearing things? Apollo talks very quietly. So du equals e to the y dy. And so we do that. He just appeared.
Hi.
Very stealth. Hi. So u sub is going to work here because its derivative is in the numerator. If we let u be this part in the denominator within the parentheses, the derivative is in the numerator. So that's what makes it a good substitution. So then let's do our substitution. And we are converting, so we're going to use some sort of placeholder limits. E to the y dy, that's du. And then in the denominator, we have u to the 2/3. Very nice. Very simplified integrand. And if we want to integrate that, what is the strategy with that u to the 2/3 in the denominator?
Power.
We're actually going to move it up. If we have any power on that u in the denominator other than 1, we move it up. If it's a 1, it's a natural log automatically. So we make it u to the negative 2/3. And then we use the power rule. Placeholder limits. So power rule, we're going to get u to the 1/3 multiplied by 3. Good. All right, so power rule. And then we go back to our original variable, our original dependent variable. So we're going to go back to y. The 3 can come to the front, so we'll have 3 limit. And then the u is being back substituted into e to the y minus 1. And that's raised to the 1/3 power. Now we can go back to our original limits, which were c and ln of 3. Now we evaluate. Any questions up to that moment before we evaluate? Feeling good?
Is there any times where you're not going to be using u sub, or is it always going to be u sub?
Well, if it's a really, I mean, to have an improper integral with trig sub, that's kind of a lot of, that would be a big, long problem. It's very common to see improper integrals with u sub or even PFD, a simple PFD. Probably not a trig sub, though. I mean, you always check u sub first anyway, just to see if it's a good technique. All right. Now we plug in our limits. So we're going to have 3 limit. So limit of integration, upper limit, e to the natural log of 3. 3 minus 1, 2. So we have 2 to the 1/3 when we plug in natural log of 3. Now let's plug in c. So we're going to have minus quantity e to the c minus 1, quantity to the 1/3. And this limit is as c goes to 0 from the right-hand side. And what is the limit of that whole business? Say it out loud, Eliana.
It's 2 to the 1/3.
Oh, you're an angel. So this part is going to 0, because if we plug in 0 for the c, e to the 0 is 1, 1 minus 1 is 0. Yep, exactly. And so anytime we have a limit at a constant, we always plug that constant in, and if we get a value, then that is the limit.
What do you mean limit at a constant?
So this limit is at a constant.
When would it not be at a constant?
Like if you had a limit at infinity.
Oh,
You can't plug in infinity. But if you have a limit at a constant, you plug that constant in, and if the constant results in another constant, then that is the limit. Because what that means is that this function here is continuous at that constant, which will give us a value.
So if it was infinity, like how would you go about it?
Then you do what we were doing before. You might have to do L'Hopital's rule or something. So you can't just plug in infinity. So if you have a limit at a constant, you plug in that constant, and if you get a result, then you're good to go. If you got something indeterminate, then you would have to do something different. So ideally, when you're taking the limit at a constant, when you plug it in, you get something that, you get another constant, which is the limit, ideally. So yeah, that's our area then, right there. That we cannot simplify anymore. That is not 6. That is as simple as it gets. All right, any part of that that you want to ask about?
Why is it 2 to the 1/3?
Right here.
Yeah.
So when we plug in natural log of 3 right here, e raised to the natural log of 3 is 3, and then 3 minus 1.
Oh, okay.
See it?
See the minus one.
Because 3 minus 1 is 2. Yeah. It always boils down to something moderately obvious.
How often do you see 6 on the test?
More often than I'd like to admit. That is unfortunate. Please. But this class won't do that.
Don't jinx it.
Yeah, right. I didn't say anything. I said nothing. Okay, so remember, worksheet corrections are due tonight by midnight for chapter 6.
Wait, what?
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 What'd you say?
Oh, correct.
How does 8?
Which word didn't you understand?
Whatever came before corrections.
Oh, what did I do?
Not
So
this coming worksheet, the first one we did.
worksheet corrections are for the one that we already turned in. And
Okay.
if you didn't get a 5 on it, you can get more points on it. So it's not here though. Where can I see it? I might have to go into, I'm going into yours, Logan.
Why?
Because it says right here, so Monday, March 6th,
Oh, okay.
right there, March 6th.
I did that.
So if you've done the corrections, and then the second worksheet is going to be due Sunday night before the test, same as the homework, Sunday night before the test. And there's one hard part, which I mentioned last time. There's one hard part on the worksheet on the first problem. Has to do with an absolute value. Let's just talk for a second about, let's look at an example. If you haven't done this yet, then this will be really important. So if you have something like y equals the natural log, let's just suppose you have x minus 5. It should be clear by now that the absolute value function is piecewise defined. So let's look at a non-related piecewise defined function and talk about the derivative of it for a moment. Let's suppose we have this function. So this is a piecewise defined function. It's defined differently for different pieces of the domain. And if you were to differentiate it, the derivative is a piecewise defined function. Right? The derivative would be that kind of thing. And so normally when you have a piecewise defined function, the expectation is that your derivative is probably going to be a piecewise defined function also. Now that's normally what happens. But let's look at this special case here with the natural log of an absolute value. So if we were to write this as a piecewise defined function, we would say that this is natural log parentheses x minus 5 if x is greater than 5. Right, if x is greater than 5, then the inside is positive, so the absolute values are unnecessary. And otherwise, so if x is less than 5, we multiply the inside by -1. So then we would have that. So if x is less than 5, we do that multiplication by -1 thing. Everyone okay with that? So if you plugged in, say, 4, now you have -4 plus 5, that's positive, no problem. And 5, of course, gives you undefined. Natural log of 0 is undefined. So now let's go ahead and find derivatives of this piecewise defined function. So y prime, derivative of this is what? 1 over the inside. The derivative of the inside is just 1, so we don't have to deal with any chain rule business there. And then what about down here? 1 over the inside multiplied by
-1.
-1, because that's the derivative of the inside. But if you push that -1 into the denominator, you end up with, these are the same. So you can, in this particular instance, say that the derivative of that is not a piecewise defined function. It is got a unique derivative. So even though the function was piecewise defined, its derivative is not. So that's going to be important for the first part of worksheet for chapter 8. So keep that in mind. You're going to be doing integration by parts, and when you're doing the integration by parts, you're going to end up letting the u equal a natural log thing, so you have to find du, and it's going to involve an absolute value. So keep that in mind. That'll help you a lot. Any questions on that idea? All right.
I have a question on where we check how many points we got on the worksheet.
Can I pull your section up, or
Yeah.
do you care?
No.
Let's see. There. So under worksheets, if we go to chapter 6, it will tell you, you got 5. Nice job, Alex. So you have no corrections to do. Yeah.
What did I get?
You have to do something to get something.
I finished it in the corrections.
I haven't graded the corrections yet.
Why not?
Why not? Because they're not due till tonight. I'll grade them once they're due.
Fine.
I almost called you an overachiever.
Oh.
Okay, so we're going to go to chapter 9. 2 sections in chapter 9 only, 9.1 and 9.3. So we are only going to be looking at the very basics of differential equations. You can read this paragraph on your own time. This paragraph tells you basically that if there's one topic in math that's common to a bazillion fields of study, it's differential equations. Differential equations is everywhere. Why? Because differential equations are equations that measure rates of change. And that's what the world is doing, right? Everything's changing, and we want to predict the future because we're greedy. We can predict the future, we can make money. And so differential equations are everywhere because you're trying to predict, what's going to happen with different things. Whatever it happens to be. You can be looking at electricity, you can be looking at water, you can be looking at gas, you can be looking at pollutants, looking at population. All of that is differential equations. And it's very easy to go out in the world and measure things. But then the math is to take those measurements and find a function that satisfies those changing rates so that then you can predict the future with that function. Like we did earlier. Are you making noise?
No.
So like we did earlier with that the population models. Right? So that's the same idea, right? And it's just that it can be it's across the board. Okay, so what we want to do just now is understand kind of some basic terminology and actually understand that you already have been solving differential equations since you started integration. Integration is the way you solve a differential equation. So first thing, the order of a differential equation is the highest order that appears on a derivative in the equation. So this equation here, this differential equation is linear because this is the highest derivative that appears, and it's to the first order. This equation right here is quadratic, or second order, because the highest derivative that appears is the second derivative. So the order of a differential equation is just the highest derivative that appears in the equation. A differential equation is linear. Every field in math from here on out has a whole different definition of the word linear. It means something totally different in every class from here on out. So a linear differential equation is when the function and its derivatives only appear to the first power. So we don't have y prime squared. We don't have y times y prime. So the powers are to 1, and there's no commingling of the function and its derivatives. So when we look right here, this is linear. We've got the derivative, y prime, right here, raised to the first power. Y is raised to the first power. So there's no square root of y. There's no square root of y prime. There's no y prime cubed. So all linear means is that the function that we're trying to find, that's the whole goal, is to find this function y. I'm making noises.
I'll explain that.
Oh, it's from my son. What? Calc 3 question?
Should we all help him solve it?
Yeah.
Yeah,
Easy.
he's on his own. So down here, each one of the function and each of its derivatives, again, raised to the first power. Right? So that's going to be considered linear. And linear those are going to be the easiest type of differential equations to solve, of course. You hear the word linear and you know it's probably one of the easier types. So that's the first type you study in differential equations. Everything's got to be linear. And these coefficient functions, these functions of t, they can be as crazy as you can imagine. And it does not affect whether it's linear or nonlinear. So those coefficient functions, in this case p, q, r, and g, they can have square roots, they can be trig functions, they can be any number of bizarre things. Doesn't matter. The classification of order and linearity just depend on the y's and the y, the y prime, the y double prime. Doesn't matter what the t's are doing. Okay, so let's take a look at some simple ones. So here is a differential equation right here, and they are giving us a solution. And they want us to say, verify that that truly is a solution here. So there's nothing complex here. All we're doing is verifying, just like you did way back in algebra when it said, verify this ordered pair is on the curve. You just plugged it in and checked to see if you got a true statement. Same idea. We're going to take this function, its derivative or derivatives, plug it into the equation and see if we have something that's true. That's it. That's how we check. So keep in mind, we have not talked about how we find this function yet. We'll do that in a minute. So there's the derivative. And now we're just plugging in to see if it satisfies the equation. So we have t multiplied by its derivative minus 3 times the function that they're claiming is a solution to this differential equation. We're going to put a question mark there because we don't know. Is it true or not? And sure enough, over here we have 3c times ty squared, 3c times, I'm missing something. Let's see. Oh, why is that a y squared? Because what should that letter be? T. When we differentiate t cubed, we should get 3t squared. Thank you. There we go. So now on the left here we have 3c times t cubed. On the right here we have 3c times t cubed. We're subtracting, so yeah, we get 0 equals 0. So that checks. That means it is in fact a solution. Now one question you may ask, so there's an infinite number of constants you could plug in there, and any one of them will give you a solution. They will give you, bless you, a particular solution. If we plug in c equals 5, that's going to give us one particular solution from this entire family of antiderivatives. Okay? Now one question you could ask is, Are there other solutions to this differential equation? Or do all of them have to be of this form? And that's something you'll learn when you get into differential equations. There's something called the existence and uniqueness theorem. And there's a couple of rules that if they hold up, then there's going to be only a unique solution. There's not going to be other weird solutions that are perhaps not obvious. So, at this stage, you can think of this as the solution. Any solution to that's going to be of this form. All right. Here is a second order differential equation. So here's the differential equation right there. This one has this function that's given as a solution. And now we have initial values here. So notice that this solution is particular. They resolve the constants of integration. If you were going to solve this differential equation, it's a second order, so you would end up with two constants of integration, just like we did earlier in the semester. If you start with acceleration is minus 32, you integrate, you get velocity with a constant of integration. You integrate again, you get position with a second constant of integration. So if you have a second order, you get two constants of integration. So you would need two initial values to resolve the constants. So let's check. First, let's just make sure that these initial values are in fact true. Well, let's take the derivative first. Then we'll double check. Because this one, we need the derivative. So let's take our derivative first. So y prime, derivative of cosine is minus sine. So this is going to be 9 sine 3t. So let's just check our initial values and make sure that they're not trying to pull one over on us. Y of 0 is negative 3. If we plug in 0 right here, cosine of 0 is 1. 1 times negative 3. So that initial value checks. So they didn't goof up with the initial value. And now let's check over here. Y of 0 is 0. If we plug in a 0 for that t value, sine of 0 is 0, so y prime is 0. So both those initial values check. Now let's check the function and its derivatives in the actual differential equation. So first let's find y double prime. So y double prime will be 27 cosine of 3t. Let's plug it in. So we're going to have 27 cosine of 3t plus 9 times y something seems fishy to me. Oh, I'm looking here. I should be looking there. 9 times negative 3. I'm like, wait, that's not going to be 27? Panic. Okay, so plugging in y, not y prime. I was staring at that. 9 times 9 is 81. That's not what we want, though. We want this. And sure enough, we have 27 cosine of 3t minus 27 cosine of 3t. Does that equal 0? Yes, we get 0 equals 0, so that checks. So that tells us that that equation is, in fact, the solution, that function.
How does he get 27 cosine?
In the middle here, whoops, that's 27. This one here?
Yeah.
So we plug in y double prime right there, and then 9 times y, there's y, so it's 9 times negative 3. So we're plugging this function in for the y value right there. So it's going to be 9 times that, which is negative 27. And then they cancel. This will not be on the test.
Thank you.
This is just sort of understanding some basic terminology. Plugging in the function and its derivatives and deciding whether you get an equality. So, let's solve a differential equation. If we have the derivative on the left, what do you think we do to both sides? Integrate. If you integrate both sides of this equation with respect to t, you integrate that side with respect to t, and you integrate this side with respect to t, the integral of a derivative is the function. And on the right-hand side, we get 3t minus e to the negative 2t divided by 2 plus c. So that is the general solution to the differential equation that was given. In other words, the way you solve a differential equation is to integrate. So there is our general solution.
That sounds too easy.
So no mysteries. So it is called a general solution because of the c right here. So it's general. We don't know what the c is. There's an infinite number. There's a bunch of parallel functions that satisfy this differential equation. If they give us initial values, then we can resolve the constant and get a particular solution. So normally, the solution to a differential equation, you're visualizing a whole bunch of concentric curves or parallel curves or a bunch of curves that don't intersect typically. And if you want one of them, you find that one particular solution by resolving the constants with the initial values that they give you, if they give you. Yeah?
So, like with that c, we've traditionally been able to, multiply it by 2 or divide it by 3 or whatever, and it's still c. In the previous example, we left a constant multiplied by our general constant.
Yeah, and that is important because in this case, we are using the original c right here when we plug it into y. So if we were to absorb this, then we'd have a second constant. So we don't want a second constant here because the constant we start with is actually going to be used. So in those scenarios that you're talking about, the original constant we never use again. Whatever we get down to in the very end, that's the equation that we use when we plug in our limits of integration or whatever we're doing. We don't need to go back to the original constant. So here, the constant that we start with is being used in this, so we don't want to change it. Yeah.
Thank you.
Yeah. All right, so one more of this basic kind. So this is identical to what we did way back in chapter 6. We just integrate twice. Bless you. So when we integrate both sides, the integral of y double prime is y prime. So we're integrating both sides with respect to t. Usually we don't draw the integral on this side. You can draw that if you want, but if we integrate both sides, this is the next step. So we integrate the right-hand side. And I'll put a C1. I know that we're going to have two constants of integration. So there is y prime. Now our goal is to get to y. So we just integrate a second time. Integrate. Integrate. So if we integrate both sides, we will have that y prime becomes the integrand over here. And y will equal 2t to the 6 minus 2t squared plus 6t to the negative 1, which is 6 over t, plus c1t plus c2. So that right there is the general solution.
Would specific have a solve along the way?
So a particular solution, we would have initial values and we could solve for the constants along the way. Yeah.
So we can't just mush the constants together anymore?
And we can't here because this one has a t. Yeah, we won't mush them together here. Yeah. And when we're integrating, there's never going to be a constant plus a constant. Right? Because when you integrate this constant right here, you're going to end up with a t, so you'll never end up with constants that are like. You'll always have a different power of t.
Is that C1 times T?
Yeah.
Plus
Yeah.
C2?
Yeah, C1 next to t. C1 times t. All right, we're almost done with 9-1. You will find differential equations easier than Calc 2 or easier than easier than Calc 3. It is Calc 2 and Calc 3 are kind of the crest, and then DiffyQ, linear, they are easier.
Wait, why do they do that to us?
That's a complicated question.
We have time though.
Complicated question. In order to do anything real in science, you got to get through Calc 3. And so they jam it all into the first 3 semesters.
Don't they just hate us?
No, they have your best interest at heart.
My money?
Perhaps. Okay, so this one is and usually you'll see them written as IVPs, initial value problems. So some sort of IVP, it's just a differential equation with initial values. So same idea. We're going to integrate both sides. So the integral of the right-hand side that's what y is going to be. These differential equations will get harder fast, trust me. Right now we're sort of understanding the concept. And a basic differential equation where you can isolate the derivative all by itself. Notice that we just have a y prime. We don't have a y anywhere. So that's what makes these fairly easy. There's no y, just a y prime or a y double prime. And so when we integrate here, this will be our general solution. That's our general. So general, there's another word that's not going to really matter here, but this is also considered an explicit solution because we were able to solve for y. So if you can solve for your dependent variable, we'll call that explicit in contrast to implicit, which we'll look at the difference soon. And it's general because of that plus c right there. Now this has initial value y of 0 is 4, so now we do the standard initial value thing. This says that when t is 0, y is 4, so we do what you think we would do. Do that. Cosine of 0
Is negative.
Cosine of 0 is 1, so we're going to add 1 to both sides. We'll get 5 is equal to c. And that gives us the particular solution. So this solution is particular to that initial value. So that is a particular. If we have initial values, we can get one function, not a group of functions. When you have that c, you have a whole group of functions. All right, you all try this initial value problem, solve this differential equation. It's got a product in it, so you'll have to use what technique of integration? Parts, multiplied voodoo. Sure. As long as it's not like before.
Yeah, I just totally forgot, so I have like this ladies only skiing
Steamboat.
Steamboat. Yeah, I scheduled it for the semester and I like checked the dates for my physics class, but it's fine, I didn't think to check.
Yeah, totally fine.
It's like that's not important.
It's a bluebird.
No, yeah,
Yeah, it's run by this like female-owned coffee shop. They just like rented out the whole.
Awesome.
Big-
So, what time do you want to do?
Yeah, exactly. I would love to like be able to leave this area around noon-ish or something.
Yeah, the testing center opens at 9. So you can just take it right at 9.
Yeah.
I just broke twice at
Send me, yeah, send me an email. Yeah, totally. Send me an email though, so I have it in my inbox. I'm sorry to do this.
Yeah.
Oh, make sure it's there.
Yeah.
Did I choose the right one?
No. Because isn't it getting worse? If you put the T with the DV, you integrate and you're going to get a higher power. So you want to put the T with the U so that it cancels.
Because E to the T is circular, you go forever. Forever and ever, amen.
That's not right there. This is going to take integration by parts. Yeah, so well, we can't divide by T, so if we want to integrate T e to the T, this is a product. So we're going to have to do the UdV equals ultraviolet UV. So we have to do that. So whenever we have a product, it's very rare that we know the antiderivative of the product. And so we normally would try to do U sub, and that will not work often. So then we have to use. No, T is not a constant. Wouldn't it be? T is the independent variable.
Oh, so treat it like an X.
Yeah. Treat it like an
I
X.
don't know, that's what I'm not.
X and T are.
Yeah, just be E to T.
Say that again. The integral of e to the t is e to the t.
I wrote it to the X.
No, it's minus.
Yeah, that's right.
You just put one.
1 dx.
Okay. So
Or
just
dt.
dx or dt.
Yeah.
Minus the
Yeah,
integral
that's what I
of
got.
dt. And then uv minus
UV.
integral of vdu. And when you do the vdu, you have no more t anymore, so you're going to be integrating just e to the t. Yeah, well. uv minus integral of vdu.
At minus
Integral of vdu.
UV minus integral.
for the first. That's the only white part.
Yeah.
And so that.
Yeah, and you already did it, so you don't need to do it again.
Same exact.
Because the integral of ET is ET.
et.
It's gonna be
No.
same expression.
It looks pretty darn good.
I did a correct.
Yeah, no, that looks good.
Okay, cool.
You do the second one?
Yeah, you
I
have
don't
to.
want to do ultraviolet vision.
You should only have
but
one.
So what I did was I solved.
Or are we trying to get to Y prime?
No, we are going all the way to Y. But you're just
Rewrite that.
it's happening, right?
But I'm not wrong.
No, you are not wrong.
Can we not do that?
You are not wrong. In fact, I would say stronger you are correct.
So I'm at
Minus.
I'm at what?
Minus.
Why not have minus? That should be a plus.
What's the derivative of negative?
And then yours is. What you're doing is right. Unless there's a weird typo.
I would like to
see if I was
dumb.
Another one where you just take
Oh,
the.
yeah.
Those are the only two
Well,
choices.
this will say zero.
Dumb or great?
Because Mark doesn't know the route.
That's good. That's good.
Minus.
Except your
But if it's the same thing,
E to the T, we already figured that out.
Right here, right?
it's the same thing. You just write it again and then it's like
I
Yeah, that's right. But now you have to integrate again, so you have to integrate t to the t. Right. This again, and then you're gonna get a constant.
Okay, that is right.
Should be.
This one we can just like.
Should be C. Oh, did you already plug in your points? Oh, I didn't even see it. You already plugged it
It
in.
just keeps going, so it's not doing it. If I put T over here.
So you got your constant at zero?
It'll make it more complicated.
And then we got
If I take the derivative, it makes it
But
simpler.
if you plug in 0 here, you do not get 0.
minus one t.
Yeah, let's do it.
So then I get that right here, right? And then I just roll it
That
down.
minus integral
When I get
dt.
ultra and then I just took the integral here.
You and your
The
DTs.
second part, which is just e to the c.
Plus C.
I think you would just.
This is the derivative.
Now,
And then I just took the integral.
well,
of the second
something fishy happened.
term. And the derivative, the
Because
integral of b to
your,
the t is
this
t.
turns
And then
into
because you took it, it's
UV.
we have a plus c.
So this is y prime.
And now I'm solving the second part.
Okay, this is still y
Y
prime.
prime is zero.
Yeah, you have now you have to integrate
So
the
I'm
second
solving
time.
this.
No, y double prime equals, sorry.
Yep, entire, the whole, integrate the whole entire thing.
So
again.
this is, that's our y, this is 1.
And then you minus 2e to the c.
So it's, if I put in zeros for every t, it's gonna equal 1.
But
So this whole left side right here is 0, minus
Yeah,
1
this right
plus
here, when you
plus
integrate that, you have to
1
integrate that, you're
plus
not substituting in your value yet, so this should be e to the t.
So I just added, so it's 2.
No, it's an equal.
Oh, then it's an e, oh, okay, good. Yeah, so that's right. And now you integrate that whole thing again, yeah, just like that.
And then so you just.
So now that, it's this with the plus 2.
Because this is your y prime.
Alright.
Right, this right, you integrated y double prime, so this is gonna be your y prime. And now to get to y, you have to integrate.
Minus e to the t.
Now you have to integrate one more time.
Okay, with this again.
Yep, integrate that.
So I have to do
Like,
this.
that's the first
Thing
step,
again.
just so I can keep my work clean.
Yep,
And now,
or you could look above because you already did it.
Yeah, since you already did.
Yeah.
and so now we're gonna.
So you just do the same thing.
Minus 2et plus 2.
So it's just the same thing.
Plus c.
and then with that turning into a minus.
Like right here, you got that line.
Integrate that, you're gonna get a like term when you do that again.
You know what,
Then when you
yeah,
combine
this
it,
is
when
your
you
e,
plug it in
it's
again,
equals e to the t. So
I
would
forget the
repeat this whole
constant.
thing as this first
We'll
one.
look at the constant one second. Yeah,
What's the integral?
did you get a plus 2?
And what's the
I got
integral?
minus.
You get a minus 2 and she got a plus 2. Let's find out.
E to the t.
Let's do it. Let's do it, people.
Just this little part right here. is
Let's
gonna
do
equal
this.
that whole part.
So when we integrate both sides, we have this.
That's what I would get.
So the first thing, recognize that you have a product. And whenever we have a product, if U sub doesn't work, then probably integration by parts, if we have a product. And then we want to let U, in this case, be t, so that when we take its derivative, it gets simpler.
Oh, it is.
And dv is going to be e to the t dt. So the derivative on the left here, du equals dt. You did get a plus, Alex?
Yeah, it is.
And then we will have uv, which is t e to the t,
T is minus e
minus integral of v du.
plus 2t.
So that's our first integration by parts. This integral can then be done instantaneously. So that is y prime. So y prime has a constant of integration in it. Now we integrate one more time. So y is going to be the integral of t e to the t minus e to the t plus c with respect to t. And we already did the integral of t e to the t right up there. So we can kind of cut to the chase here. This is going to be t e to the t minus e to the t minus e to the t plus ct. And I'm going to put, since we have two integration constants, let's go ahead and just call them C1 and C2. You could have resolved this constant earlier, but many times they're going to ask you for the general solution anyway, so having both constants in there in some cases is going to be important. And we'll just resolve them both at once. And actually, we have one like term here, right? Yeah, let's do that one like term. So we have y equals t e to the t minus 2e to the t plus c1t plus c2. So there is our general. So general always has the constants of integration in there. Now let's resolve our constants. So resolving the first constant, let's look here. So y prime is 1 when t is 0. So 0 minus 1 plus c1. So that tells us that c1 is positive 2. And then our second constant of integration, we're going to come here, and it says y of 0 is 0. So 0 is going to equal, plugging in 0 is going to give 0 minus 2 plus 0 plus c2. So c2 is also 2. So our particular solution is going to be t e to the t minus 2 e to the t plus 2t plus 2. Match? Ian, did you get it? Good? All right. Yeah, differential equations a little bit more like algebra. You know, you kind of have a very defined procedure and you just sort of do it.
I miss algebra. Things were simple.
Back when things were simple.
It was a simpler time.
Why is it plus 2t? Like 2t?
Right here?
Yeah.
That's because our C1 is 2.
Yeah, but why is it like a t? Like, why does it have a
T on it?
Yeah.
So when you get your first antiderivative right there, when you integrate this, when you integrate that, you're going to get a C1t. If you integrate a constant, you end up with that constant times t. Were you missing one term?
Yeah. So could you not? Oh, I guess if you. I was gonna say if you put the 2 and then integrated that, you would still get the same thing, and then solve that with the other one. I see.
The other initial.
Yeah, I see. I just forgot to integrate the constant.
Right.
Yeah.
Right.
And then I could transfer to you.
All right. Let's go to next section.
I don't know.
Halfway through chapter 9.
Take that stuff here. I'm just saying.
Hey, isn't it break time yet?
No.
Why not?
Our union mandated lunch break.
Triangle.
I believe in child labor. Okay, so the first real differential equations technique that we're going to have, when it's not just straight up integration, is going to be for a type of differential equation that's called separable. So a separable differential equation is going to be an equation where we can separate the dependent variable and the independent variable. And so the idea will be that if we can put all the dependent variable stuff on the left, so with the notation that they have here, n of y dy, and then all of the independent stuff on the right, including the differential, that's separable. Okay, so what's really interesting about these separable differential equations is that you can integrate each side with respect to a different variable, and it will work. So for example, with this one here, whenever we are dealing with separable, we have to use the differential notation. We can't use prime notation. So we convert our prime notation over to differential notation. And now for it to be separable, that means we want to get dy and all y's on the left, dt's and all t's on the right. So here's how we are going to separate it. So this is what it'll look like separated. If we want to move the e to the 4t to the other side, it becomes e to the negative 4t. If we want to move the dt to the right, we multiply by dt. Now it's separated. Now we, question?
So the way you move the e to negative 4t to the other side, would it be like the same as if you moved it from the bottom to the top? Like
Yeah.
you just switch the...
Yep, it goes through this magic tunnel. When it goes through the magic tunnel, the exponent changes sign. Which is exactly what you just said. If you divided both sides by e to the 4t, you'd have it in the denominator
Oh,
here,
right.
and then it can pop to the numerator by changing the exponent. That makes sense?
Yeah.
Yeah, whatever way makes the most sense. Dividing, magic tunnel, whatever works. Anything that goes through the magic tunnel, whoo, becomes its reciprocal. Yeah, so you can think of it either way. Okay, so now we integrate both sides, and when we integrate both sides, we're going to integrate the right with respect to y, the left with respect to y, and the right with respect to t. And if, Joe, what's the integral of dy?
Not really what you said.
What's the integral of dy?
Oh, it's just,
Yeah. You learned that earlier today.
I did.
And then on the right-hand side, we have to use that reverse chain rule business. So the integral of an exponential is itself divided by the derivative of the exponent. You can put that out in front. And then we have a constant of integration. So this is now our general solution. And unless we have initial values, that's all we can do, general. That's it.
What if we can't get it over to one side?
So then we have to leave it as an implicit solution.
You sure this can't be on the test?
This will be on the test. This can be on the test. Just that plugging in the function and its derivatives, that's not on the test. Actually finding the solution, that's reasonable.
Too hard, it's too difficult.
Yeah. All right, let's do one more of these, and then we'll honor Logan's request.
Finally.
So you all try this one. See if you can separate it and find the general. Yeah?
Does it matter if dx or dy is at the top or bottom? Like when you put the...
Yes, it does. So the dependent variable is always in the numerator. The independent variable is always in the bottom. So y prime of t means dy dt. It means that t is independent. And so this means that t has to be in the bottom.
So x has to be in the bottom.
Correct. That's right. All right.
Is this supposed to be
What? Say that again? So now integrate both sides.
Oh, then it's just 1 over.
No, it's not just like that.
No, it's 1 over.
Yeah, so now you separate it. So the x's are going to stay on the right and the y's are going to go left. So you want all y's left and all x's right.
So right now,
Could you just move that dx up there?
So you time back.
Magic tunnel. Magic tunnel. Look at the magic tunnel and you're going to convert.
I don't like this.
Alright, so you change.
Yeah, that's right. Yeah, and then you can integrate both sides. Say that again. Why is it going to be a weird
But
answer?
it had to be like.
Well, we have to get to y. So we're not going to have a y originally. We're going to have something that's got it in the denominator. So yeah, you're right. So we'll try to get to y. But at first,
Yeah, it's equal.
first step there is to get these antiderivative. Those aren't separated. You're good, that's right. There's just more to do.
Yeah, I know.
But wait, how did that- oh, because the x squared is true. Let's see how you're. So you have y is -2 and x is -2. Yeah, perfect. And then a plus constant. Yeah. And now our goal, like James just said, the y is not sort of isolated. We don't just have a y, we have a negative y plus 1. So we want to do some algebra so that we get y all by itself on the left. So see if you can pull off that algebra.
I got the natural log of y.
Wrong. There should not be a natural log in there.
I forgot. My meeting.
So this part right here, so you have the x's together, the y's and the there. So when we do separation, we can't have x's and y's the same on the So you want to divide both sides by y squared. So that y squared divide it over under
I've just played around with like.
Yes.
Yeah. Which is a better way to write it, because then we can do the.
No, you matched me exactly. Well, this is 62.
Is that your stuff?
Oh, sorry.
Oh, okay.
There. It's positive, dude.
That
It's
is.
negative 2.
I don't know though. He like rearranged everything.
When you see it,
Yeah, no, I have.
Now I'm gonna
add 1 to
Yeah,
negative 2
no,
again.
that's right.
So I integrate the dy.
She sees it. She sees it. That feels a little too easy. So on this side, you're going to want to get a common denominator first. So this is correct. You want to flip everything, but you can't flip in things individually. So we want to get this all combined into one fraction. And then so you have to set it up as a proportion.
According to this thing that we wrote down earlier, we
No, take out that x squared.
So yes, the x's are going to go over there. That's a dy. And then the y, so and then your dx, if you move the dx over here, you multiply both sides by dx. Now you have to get the y's over there.
Because I did it with just the.
No.
Yep, that's what it means to be separated. Y's on the left, x's on the right. Or y's on the left.
I have forgotten to take this integral.
You better not forget how to do that integral.
I just have natural log.
No natural logs. And then a plus c. That's perfect. That's correct. That is correct.
It's just a
Yep, that is correct. So now the goal is to get, we have to isolate y. Right now we have y to the negative 1, which is not what we want. We want to do like we did over here, and we ended up with y equals. So now we want to algebra that. Algebra that to get to
I
y.
don't know if you're trying to get to like.
Yeah, so that's right.
Probably.
Yeah, that's good.
In which case you just have 1 plus squared.
I'm learning. Okay, so was everybody able to get the algebra? No. Algebra? That is right. Then you can combine those constants into one constant. So those constants you can combine. All right, so let's do this, and then we'll take a break. So first thing we want to do is get rid of the prime notation.
That could be right.
So we have that. And when we say separate, dependent to the left, independent to the right.
I see.
Is it obvious why dependent should go to the left?
So that's how we write it.
The dy is already in the numerator, right? And that's the dependent differential. If you move it to the right, it would be in the denominator, and you can't integrate it with the denominator differential. So we want to leave that alone. These x's all need to go to the other side, so we would end up with this. So the x squared is moving over, so it becomes an x to the minus 2. The dx is being multiplied over, so now it's separated. And this is where we integrate both sides. And we add 1 to the exponent and divide by the new exponent in both cases.
This is the constant. Because those two would.
Now we would like to have an explicit solution. So we want to get y all by itself. The first thing I see is that we can multiply by negative 1. If we multiply by negative 1, we can let that constant swallow up the minus 1. Because we're never going to be going back We're only going forward here, so when we're going forward, we can let constants combine. Now we can't flip this yet. You can't flip both sides unless both sides are fractions. Once you have a fraction equal to a fraction, then you can flip both sides. So we need to get a common denominator on the right before we can do that. So we're going to rewrite this as 1 plus cx over x. And as soon as we have that, a fraction equaling a fraction, then we can flip both sides, which is the same as cross multiplying and redividing. So that tells us that we end up with y equals x over 1 plus cx. So that is the form of our general explicit solution.
Couldn't CX just be C though, since it's
X is a variable.
so we have to keep the X times the C.
Yeah.
Can you do that just?
Yeah, so we can only take constants and constants and put them together, not a constant and a variable. So the variable is super important to leave. Yeah.
Can you do that distribution one more time, where you're doing the C?
This,
The one line up to get from there, it's the bottom line.
get from here to here.
Yeah.
So,
Okay, thank you.
multiply by 1. When in doubt, multiply by 1. So that is our general explicit solution. Did this have initial value? No.
You just do C over there.
Yeah, so that's it. All right, let's take a break. 10-minute break.
Instead of just doing landings.
You might be able to.
Self-portrait? What's going on here? Oh, yeah, I can tell by the nose. You can. You can. You'll still have a whole like thing in the denominator that you would have to simplify. This is not simplified yet. You can't have a fraction of a fraction. So right here, if you, in order to clear this fraction, you could multiply numerator and denominator both by x. And that will distribute across, and that will give you a negative x in the top. And distributing here, you'll get negative 1 plus cx. And then you can multiply by negative 1 again, and you'd get exactly what we have. Still some work to do, though, yeah.
Can't you just do C over 1 instead of like multiplying by x over x?
Well, if it's c over 1, they don't have the same, you know what I mean?
It already is C over 1.
So it is c over 1 already, but we need to get an x so that those denominators match. Do another initial value problem. Basic question, who can separate e to the t times y? Who can do that first?
Huh?
So we want to separate this, so my question to you, I'll do the obvious part and then you tell me the hard part.
Y, ln, v?
So let me rewrite this first and then you tell me how we separate it. I want to check on your basic algebra.
Google.
So how do we separate e to the ty?
You add it. So et.
Write it down if you think you know how to do it. Write it down. Write it down. The pressure's on.
For what?
To use lead.
Oh, we would just do
Graphite.
we'd do natural, take it apart.
Okay, so first, here's the first genius suggestion. Tell me if this is correct or not correct.
Incorrect.
Incorrect. Can you add powers with the same base?
No.
No, we can't add those powers. If they had the same exponent, we could.
Maybe.
That's what I said, the exponent.
See, we can't do that.
that works, but they're not.
Is there? What else could we? Is there a way? Is it possible?
Yes.
Yeah, it's possible.
I don't know. No.
It's not possible. We cannot separate it.
Because we haven't tried ours.
So you could. The only thing you could do is say, okay, well, what about if we do this? Right, that's legitimate. You could do that, but you still aren't going to be able to get that y off because you'd have to do some sort of root. But as soon as you do a root, then you're rooting the differential, and you can't integrate the square rooted dy or the square root of dt. Right? The differentials need to stay intact. And as soon as you are trying to take like the y root of both sides, then it'll affect the differential. So this is not separable. Not separable. Now, what about this? I'll give you this one to do that's very closely related. So, ready, set, go. That one you can do. Most of us.
It wasn't red. Oh, it's just
Yeah. He sees it.
I do.
Sees it. As soon as you see it, you see it.
Really?
As soon as you see it, you see it. Cole, you see it?
I think so.
Good.
That's what I was wondering.
I want to do this one step, but I don't think I can.
Don't break a law.
Well, there's this rule, but
Don't break the law.
the rules are extra.
Anyone having trouble? I see half the people writing and half the people shaking their heads. What do the people think?
It's just literally just eating the
Jim,
Y.
can we do it? Okay, so
E to the T times
so
E to the
dy dt, this we can make into a product.
Yeah.
Right now they're separated. Right, we've got them as two separate factors, which means we can divide.
So are you just doing the d to the y over d to the t, like, because you're not integrating it, or you're not?
Not yet.
Okay. You're just trying to get it.
So we want to get all the y's on the left and all the t's on the right, so that would be it. Right now they're all separated. And then on the left we would want to write this as e to the minus t, excuse me, e to the minus y. Now we are completely ready to integrate. So, integral of both sides. Let's come over here. What is that antiderivative on the left?
Negative e to the negative y.
Negative e to the negative y?
I played Chilla.
Negative e to the negative y. All right. Solve for y. So this is very subtle. After we divide by let's divide by some stuff first. So we'll get rid of the minus sign that's in front. That will come over here, and the c will just swallow it up. But here it gets a little subtle. What do we need to do to both sides to get rid of that e?
The natural log.
Natural log. So natural log of both sides. Oh, that's not that subtle. We just take the natural log and divide by negative 1. That's not that subtle. That's pretty direct.
Could we move the natural log in? Or not?
Say that once again.
So could we factor the natural log in? Or?
No.
Okay.
Natural log cannot distribute across a plus. If it was natural log of a product, you could turn it into a sum. And yeah, so I was thinking it was going to be maybe a little more interesting. It's not that interesting. Okay, so we got that. So that one wasn't too hard to solve for y. Some of them will get a little more difficult to solve for y. Question?
Did you factor out that negative inside the natural log?
That negative?
Yeah.
And what would we do with it?
Just to pull it out.
Well, if we factor it out, then that we just have to be careful not to turn it into like natural log of 1, negative 1 plus, you know what I mean? Like if you factor that negative out, you can do this, like that's true, but the whole idea of writing it as a product would then be to try to separate it with log properties.
I mean, could you pull it out of the natural log entirely?
No.
Okay.
Yeah, we can't factor anything out of a log. We have to use one of the 3 log properties if we're going to do anything with a log. We have to do log rules.
Lemo.
Gone. All right, one more. Yeah. All right, yeah, you guys can do this one. This one's not hard. This will give you good practice. I mean, it's not like the next one will be hard. This one's not hard.
So that could be dy over y.
That is not dy over y. That is dy over dt. Y prime is dy dt.
Well, but it becomes dy over y, right?
Oh, was he looking that far ahead?
It's possible.
It's possible. Okay. Wow.
We don't know.
This is where my self-confidence is terrible.
Well, you speak in half sentences.
Yeah.
So?
Yes.
You're my professor. You're supposed to know everything.
Half sentences. This guy. This guy. What are we doing with this guy? Yeah. Good.
dy dt.
Good.
And then it's middle.
You seen it?
I have a sense of
Just through Australia.
Well, so this y, so you have the dy or that is also a y, so it needs to jump over to the left also.
dy.
Because it's being multiplied by this t expression.
No. It's y times. Yeah. Oh, good point. Yeah. Great question. Everybody, Dan brought up a good point. This almost looks like y of 4t cubed plus 1. But that is y times 4t cubed plus 1.
Thanks, Dan.
Yeah. That could be misinterpreted easily. Yeah, good question. Yeah, so that is multiplication. That's a problem. We use the same symbols to mean different things all the time. Like in order to pair in an interval. So from context, we know how to tell.
And to like get rid of the natural
Exponentiate, yep.
right?
It's going to be, so the c is in the exponent, but you could take that e and distribute it, so you'll end up with the c in parentheses.
Oh, yeah.
Then,
That's
wait, we have to evaluate.
But this would also be correct.
Goodness, I'm so cool.
Yes, that would also be correct.
That's
Look at me go. I think I'm on a roll.
She's teaching us.
Yeah.
That looks
But maybe you'll,
Liking it.
Can you do it on a test?
Liking it. Liking it.
On Monday.
On Monday.
So this is 4.
And then where's your constant of integration?
E to the 0.
Well,
yeah,
yeah, it's going to be up there? Yeah, good. Yep.
oh yeah.
All right, let's go through this. Nothing super mysterious.
Do you take it back to natural log?
Okay, so we have that.
I am putting it 0.
And we'll end up with dy over y.
Equals e to the 0 so 4
Equals that.
I guess you're right. Yeah,
And then we're going to integrate both sides. We have to be careful with the constant of integration here. So we're going to get natural log absolute value of y.
I mean, it's the same thing as what it did. Natural log 4.
Okay. There's a very subtle, here's the subtle step that I was thinking we might see last time. A couple of you just blew right past it.
Yeah, we do.
So we definitely exponentiate to get rid of the natural log. So when we exponentiate, we end up with this. And on the right, the entire exponent is up there. You know, the entire right side becomes the exponent. We cannot just get rid of that absolute value right now. But notice what we can do on the right. On the right, do you agree that we could write this like that? Right? Right? Because a product, we add the exponents. And what is e to the c? It's yet another constant. So e to the c is a constant. So that constant can come out and sit in front like a multiplier. Very clever.
That was very confusing.
Okay.
It's just a number. It's still a number.
E to a number is a number.
That's true.
Now, absolute value of y is either plus 1 or minus 1 multiplied by the right-hand side. So it's a number times c, which is a number. So here is how we can get rid of the absolute value. As soon as we have that leading constant on the right, that leading constant on the right can suck up the plus 1 or minus 1 that an absolute value is equal to. Right? Absolute value of y is either plus 1 times the right or minus 1 times the right. In both cases, a constant times the right-hand side. So now we have our explicit general solution.
Why don't we need to plug in the y value for?
That's next.
Oh, just kidding.
Yeah, we're getting there. So we usually you're going to be asked to find the general first, general explicit, and now we want to find the particular. So that's next. Y of 0 is 4. So 4 equals c e to the 0. C equals 4. So our particular solution will be 4e to the t to that thing. There is our particular. So that is particular to that constant, to that initial value. Good? Any questions before we go to the next slide?
Wait, so where's the, why do you have 4e, or sorry, 4 equals c e to the 0 there?
Where did that come from? Is that what your question
Yeah,
is?
is that just from?
So
you just
y of
loaded
0 is
t?
4, so that says t is 0 when y is 4.
Right.
So we're going to plug in 4 for there and 0 plus 0
Yeah.
on the e. Yeah.
Hey Jim, where'd the absolute value go?
Is that a legitimate question?
Yeah, like.
So it's so hard to tell from the back of this class.
Sarcastic.
So this is either, right, this is piecewise. This is either y or negative y. So in either case, you have a constant times y. So what we're thinking about is that's a plus 1, that's a minus 1. Either way, it's a constant times y, and that constant can get sucked up into this constant since this is multiplicative.
Okay.
Right, so as soon as this comes down, like here we can't get rid of it.
Yeah.
Because this would either be positive e or negative e.
Okay.
But as soon as it comes down in front, that c can absorb
The C just eats it.
The c just eats it.
Okay.
Yeah. But the key is that it has to be a multiplicative constant out in front.
I'll just say you always said it was a.
All right, let's go to that. All right, you all start this one. See if this one's very similar to one we already did, but so it should be really fast for you.
Oh, there's a Y.
Let me know if you're snagged on any of it. The nice thing about these is that they're not long, right?
What is it? 2.7 something.
What is the 2.7 something?
Yeah.
So you just record a while?
2.7.
Saying you have to have
Yeah, I don't want to make myself
Where's
I
the?
guess it's E to the Y.
Yeah, there's an e to the y on the left.
Because it's under.
Yep, that's right.
Yeah, and I'm just making a whole bunch.
Yep.
Minus.
Good.
It's not
Good, good.
false.
So that's. That is very easy.
Now solve for y.
E to the y, dy, e to the x,
You know
e to
that
the
X.
e to the
Plus c.
e to the x dx.
Yeah.
Well, you would think.
Yeah, that's good.
Oh.
Way too simple. I was thinking it was like this,
This part trips me up.
but I guess
Feels
because
too easy. Like, it's
Differential
not like
equation-
a sneaky minus y.
Yeah. But now you still have to solve for y, so it's going to get a little tricky. Not much.
Yeah, the same. Like you said.
So how are we going to get rid of that e?
E to the like equals.
Take one of those sides.
And you get
Oh, plus c.
So when you take the natural log of this side, you get just y, right? And then that stuff's all inside the log, so make sure you have your parentheses there. Yeah. Is that kind of, let's find out.
Oh, yes.
E to the x plus c? That's what I thought.
All right, so there's the first step, just getting rid of the combined x and y in one exponent. And then we're going to end up with e to the y dy equals e to the x dx. And then we'll integrate both sides. So we'll have e to the y equals e to the x plus c. And then we're doing what to both sides?
Natural log problem.
Yeah, if we take the natural log, that's going to isolate the y. Can you do any simplification on the right?
No.
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 None. So that is the general explicit solution. Now for the initial value, we know that y is going to have a value of natural log of 3 when x has a value of 0.
Is that plus e or plus c?
You can't
C.
log.
So now how do we solve for c there? Add 2. Well, yeah, 2 is going to be, you're jumping steps. Woo!
I am?
So now, please don't think of that as division. We're not dividing the natural log away. What are we doing to make it disappear? E. We're exponentiating. So we're exponentiating right there. So that's how those cancel. And that tells us that C is going to be 2. And therefore, the particular solution for the initial value given is that. You see where you're getting your minus sign on?
Because I thought e to the 0 was 0. No, yeah, no, that's right.
All right, any other questions on that one? Good?
I could, but then why do I?
More of these on the
There will be a separable one on the exam.
And if there's an inseparable one,
Like, I just want to go see them.
Okay. All right, this one is a PFD. So go ahead and do this one. You should be able to do this PFD really fast. Both factors are linear.
Say what?
oh, okay, thank you.
Both factors are linear.
That's what the Navy did.
So this will be a PFD.
I don't know why.
You seeing it?
No.
So separate it.
Oh, it's going shit.
Separate it. Separate it.
Why squared?
Wait a minute. That is shenanigans. That is ridiculous. Eliana, tell him.
I don't know, it doesn't matter.
separate
fractions?
Oh my
Not how you do it.
Why?
Cool? Yeah.
Okay. Yep. I always mess up at places like that, and then it ruins my.
Yeah, no, that's good, because you've got to get the first step right to get the second step right. So now get your y's to the left. So how are you going to move these y's over to the left? This is all multiplication now, so how do you undo that?
So as you get
Right?
dy,
The d, same thing, as it's easy and multiplied by dy, so you move it to the right.
Yeah, that makes sense. Sure.
So, wait.
what'd you get for your final?
Can't distribute, this can't distribute on a plus. Natural log.
Okay.
You wish. Freshman dream.
You're on the right track.
Freshman dream.
What was that again?
What's that?
Freshman dream?
Distributing the natural log. Because we're going to end up, because you want to move it to the left. You want all the y's on the left. Now factor that, and use PFD.
I don't know. The first one is jacket. Why would I get Oh, unless you have the DT.
DT over T.
Yeah, yeah. I would make up my.
Yeah, so that's how you're going to have to go PFD,
Personal flotation.
Yeah. That's all I care about.
Yeah, I'm laughing at PFD, personal flotation device.
Jane, you got the
I did. It's all my jokes.
It's okay.
I know, that's what
I'm getting good class. You're good?
So that's normally you're in calc physics tonight, like, no one talks in any other group. It's just me and Gerardo being like, what?
Bobby
Bobby
and Zach.
and Zach. It's like Anthony, Bobby, and Zach are just in an argument triangle, and we're just like,
Because that side has a product, right? It has a y times a y minus y plus 1 in the denominator.
From like the.
And that divides over. You can't separate,
And like
you can't separate that y.
It's like class.
Totally not legal.
really?
Really? That is a freshman dream also.
Get Leona, she gets angry.
Yeah, so that's, and so now.
She owns
That form. If we had a denominator.
I don't know what to do.
That's where we start to.
Alright, so I just,
Anytime we have a y plus 1.
Who was that?
I don't know if
Who's all those guys?
Those are my sisters.
That's a master strategy.
Yeah. This part,
You guys were out there. You guys were out there. That's beautiful.
it'll be a.
You know what you guys?
Oh, yeah.
I'm like, I don't know what that is.
Yeah, the one thing that, like she's saying, is you want to think of this like separate from that.
But basically, if you have.
When you integrate the left to the right side, you're good. But integrating the left, you're going to have to do the side. Yeah, exactly. Yep, yep. And that will have an integral in front of it.
I know.
You probably got I assume Anthony had a ton.
Your move. No. That's not a log form, right?
No.
If you had in the numerator 2y plus 1, that would be true. Remember, the only way we get a log is the derivative of the log.
You guys are playing.
right? So that you're going to want to factor this again. That one's good. Yeah, that one's good.
What if it was obsessed?
Right side.
Roberto.
I would never.
No faking.
Yeah, that's
Instead of
no next though. That's
That's crazy. Directly.
that numerator's not zero.
I'm just gonna say.
Oh, you're doing the. But that's still just one. All right, people. There are some interesting dreams out there. Interesting dreams. So when we separate the variables, we are dealing with this. So the variables are separated. Multiplying out the left-hand side makes no sense. Right, Ian? Makes no sense.
Not at all.
Right. Because if we multiply that out, we
Why should I plus one?
are putting ourselves in a position we have a quadratic that's, we can't, like we can factor it, but there's no antiderivative for that. That is not a log. Logs only happen when the denominator's derivative is up in the numerator. So this doesn't turn into a log. So that's not going to help us. The whole point of having it factored is that we can integrate the left-hand side with partial fraction decomposition. So the right-hand side, everyone looks pretty good on the right. This is going to be, if we integrate both sides here, this is going to be natural log absolute t plus c.
Yes.
But the left side is going to be the integral of a over y plus b over y plus 1 dy. So that's the PFD part. If your denominator factors into linear factors, that tells you go PFD. If you can factor it into linear factors. So then we come off on the side to do the PFD part. So we have a over y plus b over y plus 1. That equals 1, right? That is 1 over, I don't know why I put it on the other side. Usually we write it the other way. Let's write it the way we normally write it. So we're taking that. Multiply both sides by the denominator. So we're going to get this.
Yeah, all five of them are formal complaining against the director. Yeah.
All right.
However the hell you.
Is everybody seeing that part? Jardo, good?
Yeah, yes.
And then what are our convenient values? Negative 1 and 0. So we're going to let y equal 0, let y equal negative 1. And that will, when we plug in 0, we'll have 1 equals a. When we plug in negative 1, we'll have 1 equals negative b. Any questions on getting those values? So the left-hand side back over here, we have a over y minus b over y plus 1. We've already got the right-hand side integrated. And now on the left-hand side, we have two different natural logs. Both of these are in log form. The derivative of y is 1. The derivative of y plus 1 is 1. Those are in log form. So this will be natural log absolute y minus natural log absolute y plus 1 equals natural log absolute t plus c.
That's not it.
So that is an implicit general solution. But we would like an explicit general solution. So we have to do some algebra. Dustin's all excited. We're going to do some algebra. So left side turns into log of a quotient. So we've got that. What?
Where you will.
So log of a quotient. We're not multiplying by e. We're exponentiating.
Log disappears.
So exponentiating. Come on, Meeps. Meep, meep. Math peeps. Everyone agree with that?
C comes down.
So c is going to come to the front because we're going to use our laws of exponents. This is e to the natural log of absolute t multiplied by e to the c. So this whole thing will be c absolute value of t. Right, the e and the ln, those undo each other, so we have absolute t. E to the c is just a constant. This can then even be simplified further just to ct, because absolute value of t is either plus t or minus t. Plus t and minus t, that's a constant times t, so that constant can be sucked into the c. All right. Now on the left side, we also have an absolute value. Well, that plus or minus 1 from this absolute value can also be stuck into that c. All right, we're getting closer.
I used to hate the C, and now I love it.
Now you love the C. You can do so many things. It's like, yeah, it's just so, it's so powerful. Okay, so now how do we solve that for y? What are we going to do? The tunnel. We'll go through the tunnel. Not the Eisenhower tunnel. Ugh.
Why? It's so loud.
All right, does everybody agree with this?
Or it's one of the atoms. The other
If we multiply both sides by y plus 1, we've got that. We're just back to algebra 1 right now. We just collect like terms, factor, divide. So pull all the y's to the left. Like terms to the left. Like terms to the left. Factor. Factor. Divide. Algebra? Right?
I don't remember this.
It's been a while. All right, algebra step that you are not 100% clear on. Multiply, subtract, factor, divide.
So when you go ahead and multiply the y plus 1, where's the, on both sides, where's the 1 going on?
CTY, CT1. Good? All right, so this one has initial value. Y of 3 is 1. So y of 3 is 1. Come over here. We're going to plug in a 3. Everyone okay with that? So y of 3 is 1 means when y is 1 when t is 3. How do we solve that for c? Algebra.
Yeah.
Multiply, collect like terms, divide. Same thing?
Yeah.
Same thing we just did a moment ago.
My own was not the best.
Collect like terms, divide. Bless you. So therefore, y is going to equal 1/6 t over 1 minus 1/6 t, which is not simplified. A fraction within a fraction is not simplified. So we're going to multiply by 1. So our simplified, explicit, particular solution is right there.
That's so frustrating.
Frustrating?
Yeah, because you get such a nice little equation. They're all that.
Yeah, it's not. That's like pleasing.
No. No.
Nice simple answer. Little rational function.
No, I'll take the complicated. It feels like I deserve
It's,
that.
it's cute, like a little chihuahua.
No.
No.
They're not cute.
Alex, question?
Can you go over the green at the top?
The green at the top.
More.
Right here?
Yeah, like I see why you pick 0,
Yep.
y equals 0 and -1 because those are the zeros, right?
Yep, that's right.
But then how come you know, like, why is it 1 equals a?
Oh, yeah.
So when we plug in 0 for y,
For both of them, you plug it into both?
yep, all the y's. So this says plug 0 in for all the y's. This goes away because it's 0. And so then we have 0 plus 1, so we have 1a, which is 1. And then when we plug in -1 for y, this one goes away. And then we have -1 times b on the right, and then divide by -1.
And does this work for, like, all of the problems like this? Because there was some in the book where it was like, you had it kind of like that, but then you would only use the 0. So like, let's say for the a to the y plus 1, it's -1. You would just plug it into that part and not like the
You can plug it into all of them. Look and see if you can find that, because when you plug in your convenient values, you plug them in for every single one. You should be.
Right.
Yeah, I can find it.
Yeah, find it. Find it.
It was weird.
Yeah, that sounds weird.
Yeah, it's doing the actual trick.
Sounds weird.
That's
I
right.
wonder if
I can do everything but just that.
Okay, so let's, we've been doing a bunch of solutions that we could isolate y and get the explicit solution. Let's talk about some where we can't. So these solutions are going to be implicit. Let's try to understand why. So first off, let's separate our variables here. So we're going to have dy dt equals the original fraction here. And then when we multiply both sides by the denominator on the left and on the right, we end up with this. So variables are separated. We integrate both sides. And the integral on the left is y cubed over 3 minus y. Integral on the right, we're going to get 2y cubed over 3. And then we'll have one constant of integration. So that is a general implicit solution. Can you isolate y here? And the answer is going to be no. If you factor on the left, you pull out a y and you have a y squared over 3 minus 1. What are you going to do with that? You divide it. It can't combine with the other side. So there's no way that you are going to be able to peel out a y here. So this is as far as you can go for the general solution. You will not be able to get an explicit. Can't be done. Now we can find our particular though. So let's come over here to find our particular. Y of 0 is 0. So 0 equals 0 plus c. So c is equal to 0. All right, so there is our implicit particular. If you wanted to, you could multiply by 3 just to get rid of the denominator. That you can certainly do. And you could do that over here also, multiply by 3, but you're not going to be able to isolate y. Yeah?
Will we just know when it's gonna be implicit?
The question usually is going to tell you. If it says find, usually if it says find the explicit, that means you're going to be able to get to y. If it doesn't say find the explicit, then maybe you can't get to y. But if it says find the explicit, then you know you can't get there. And if it says find the implicit, it implies that you can't get to y by itself. So now let's just take a look at this on Desmos for a minute and try to remember, hopefully remember what implicit functions are. So when we look at a graph of a function, or a graph, I shouldn't say a function, when we look at a graph of a curve, sometimes there are explicit functions built within it, but you can't write down their equations. And that's what's going to happen here. So if we graph this solution right here, y cubed minus 3y equals 2x cubed. There's the solution. Crazy. All right, so now there is the curve, and what you see is that there are a couple, maybe more. How many functions do you see in that curve?
700.
You see more than most of us.
I see like a quintic just on its side.
Okay, so this relation, remember back in algebra, relation is any curve. Doesn't have to pass a vertical line test or horizontal. Any curve is a relation. And then we said special relations, those that pass the vertical line test, are functions. So this curve, this relation, has 3 functions in it. That is a function of x. This is a function of x. And that is a function of x. So there are 3 implicit functions. Sometimes when you have implicit functions, you can find the formula for them. For example, if you have x squared plus y squared equals 1, right? That is that relation. And in this case, you have 2 implicit functions. There's a function of x, there's a function of x, and here you are, whoops, and here you are able to isolate the y and find that this equation, oh, I'm still in that shapes thing. You can do this kind of thing, right? So here you can find explicit representations for each of the implicit functions. And so there you can do that. Here we are not going to be able to find the green function, the blue function, and the black function. There's no way we can peel this apart and get a y equals for each one of those. Now, one thing we know is that the initial value is 0, 0. So this is the curve. Let's use that gray. This is the curve right here that we're looking for because that initial value is right there. So that, right there, that blue, that is the part of this implicit, of this curve that we want. That's where the solution is, on that blue part. But we're not going to be able to write it down explicitly. So we have to leave it implicit if we can't isolate y. Here's another one that we will not be able to find y. So let's separate our variables. So we're going to have y multiplied. I'm going to pull, let's do this kind of more at once. So we've got that. So the y's I'm multiplying over to the left from the bottom denominator on the right. And then we're going to integrate both sides. Now on the left side, we have a lot of multiplication we have to do here. So this is going to be FOILed out. So that's going to be y to the 4th multiplied by y is y to the 5th. And then the middle term here is going to be 4y squared. So 4y cubed. And then the last term here is 4 multiplied by y, we get 4y. And over here, we get x squared plus c. Integrating on the left-hand side, and we don't have to add another constant, we'll just think of it as being smushed into that one. So there is our implicit answer. And we are not going to be able to peel out a y and isolate y in this case either. So the only option is to give our implicit curve. There's our implicit curve. And if we come over to our initial value, that says that y is equal to -1 when x is equal to 1. So we're going to have -1 to the 6 over 6 plus -1 to the 4. Actually, we don't need that as a... And plus 2 times -1 squared. And x is 1, so we're going to have 1 squared plus c. So we can solve for the constant to get the particular curve that goes through this ordered pair. So we'll have 1 over 6 plus 1 plus 2 equals 1 plus c. And whatever we get there, 13 over 6 it looks like. Alex?
How do you know x is 1?
Y of x equals -1. So that's the x value for that y value. So this says when x is 1, y is -1. So it goes through the point 1 comma -1. So this family of curves, you're imagining this infinite collection. They're like concentric curves all over the place, not intersecting each other. One of them is going to go through this point. The one that goes through that point is going to have equation. And again, if we wanted to, we could multiply both sides by 6 if we want. It's not going to change much. But if we want to clear out the fractions just because we hate fractions, either one of these would be completely correct. So that thing right there, it's a curve. We know it's a curve. And we know that there's going to be implicit functions within that curve. So if we go look at the implicit functions, we will end up with, oh, I want these to be x's. Oh, no, they can be y's. Getting weirder. weirder. All right, so there is a picture of our
You have a
curve.
negative on that 6y to the 4.
Is it a positive? Thank you. Now what's it going to do?
You should do it. So
I need
page
glasses.
difference.
That looks like a cut entry.
All right, so now are we on the top or the bottom? Let's look at our initial value. Our initial value said 1, -1. So x is 1, y is -1. So 1, -1. So 1, -1 is that point right there. So the curve that we are looking for is that one right there. Obviously, we cannot isolate the y and find the equation. So all we can do is write it like that. So this. So right there, there's our ordered pair. So this is our solution right down here. We're not going to be able to pull it apart. So it looks kind of similar to the circle, though. Up here, there were 2 implicit functions, and we could pull it apart and get an equation for each. Here, it looks similar. There's 2 implicit functions, but we're not going to be able to pull it apart and solve for y. Too complicated. Impossible. Not just complicated, impossible. Can't solve for y. Okay. Last page. We'll do this one together because there's not enough time. Okay, so multiply both sides. So we're still doing the same old thing. We're just trying to separate. So put all the dependents on one side, all the independents on the other. And then integrate. Let's multiply this by 2 just to clear out the fractions. So that is our implicit general solution. Go ahead, Al.
So when you find the antiderivative of y, is that never going to get a plus, right?
You could say to yourself that both sides get a plus c, but then you would just combine them into one.
Oh, I see.
Right, so you can think of it that way.
But it technically does.
Yeah. So then
Because you're T, yeah.
there is our implicit. If we want our particular, y of 0 is 4. So that says that when x is 0, when x is 0, y is 4. So we plug in x equals 0, we plug in y equals 4. We get that c is equal to 16. So if we put everything on one side of the equation, we're going to get that,
Which is a circle.
which is a circle.
With the radius.
Now, so this is a circle. The solution, though, let's draw this real quick. Oh, yeah, circle. So circle of radius 4. And where is the initial value? 0, 4. So right there. All right, so if we wanted to find the function, that's on the top half of the circle. So here we can find the explicit solution because we know how to solve for the top half of the circle. So this top half equation right there, we know that that's going to be y equals the positive square root of 16 minus x squared. So in this case, we can find an explicit particular. So this is explicit, and it's a particular. This one is an implicit particular. What's that?
There's 4 different types. Implicit general, like explicit general.
Yeah, that's right. All right, so we will do a bunch of reviewing on Wednesday. So you could do the MyMathLab practice assignment for the exam. We'll go over those problems. Come with whatever questions you have, and we will go over them. It's that time. We are halfway through the semester.
No, we're not.
Right now.
No, we're not.
Yeah, we are.
No way.
Halfway through. Believe it or not.
Only?
Only. You still have another series.
I know, I'm so stoked it's coming out.
Infinite series
You know?
are coming. All right.